In a single snapshot, the James Webb Space Telescope has captured a swirling galaxy cluster forming just 300 million years after the Big Bang, its infant stars glowing like embers in the cosmic dark. These images, analyzed by researchers at the University of North Carolina at Chapel Hill, reveal structures that challenge our understanding of how galaxies birthed themselves in the universe's earliest days. What's most astonishing isn't just the scale of these formations, but the sheer number of them. Hidden behind cosmic dust, Webb's infrared eyes pierce the veil of time, uncovering thousands of previously invisible galaxies, each a potential cradle for new stars or even planets. One image alone holds evidence of a star-forming region so dense it defies current models, its light traveling over 13 billion years to reach us. This isn't just a glimpse into the past, it's a map of the unknown, a cosmic library of secrets waiting to rewrite the story of how the universe grew. And the telescope's journey is far from over. Each new image promises to unravel more than we ever imagined. The James Webb Space Telescope has captured images that reveal an astonishing amount of cosmic detail previously hidden from human eyes. These images, analyzed by researchers at the University of North Carolina at Chapel Hill, demonstrate how much of the universe remains to be uncovered, offering a glimpse into the early cosmos and the processes that shaped it. While the telescope's primary mission is to study the formation of galaxies, stars, and planetary systems, its latest findings underscore the vast, unexplored frontier of astrophysics. What we see in these images is not just a collection of distant objects, it's a window into the universe's past, a testament to the power of technology to peer beyond the limits of human perception. To understand the significance of these discoveries, it's essential to consider the telescope's unique capabilities. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, Webb operates in the infrared spectrum. This allows it to detect light that has been stretched over billions of years as the universe expanded, enabling astronomers to peer back to the earliest epochs of cosmic history. The telescope's advanced instruments, including its segmented mirror and sophisticated sensors, are designed to capture faint, distant signals that were previously beyond our reach. These tools have already transformed our understanding of the universe, but the latest images suggest there is far more to uncover. The images released by the University of North Carolina team highlight regions of the cosmos that were once obscured by cosmic dust or too distant to observe with earlier technology. For example, Webb's infrared vision has revealed intricate details of star-forming regions, where massive clouds of gas and dust collapse to birth new stars. These regions, often hidden from view in visible light, now appear as glowing nebulae with complex structures, offering insights into the processes that drive stellar evolution. Additionally, the telescope has captured distant galaxies that existed just a few 100 million years after the Big Bang, providing a rare look at the universe's formative years. These galaxies, some of which are only a few thousand light-years away from us, are not just distant, they are ancient, their light having traveled for billions of years to reach our instruments. One of the most striking aspects of these images is the sheer scale of what is being observed. The telescope's high-resolution cameras and spectrometers allow scientists to study the chemical composition of distant objects, analyze their motion, and determine their age. For instance, researchers have identified the presence of heavy elements in young galaxies, suggesting that the universe was already rich in complex materials shortly after its formation. This challenges previous assumptions about the timeline of element creation and the processes that governed the early cosmos. Moreover, the images reveal structures that were previously thought to be impossible, such as the intricate web of dark matter that influences the distribution of galaxies. These findings are not just theoretical, they are based on direct observations that are reshaping our understanding of the universe's origins. The University of North Carolina team's analysis of these images also emphasizes the role of technological innovation in advancing our knowledge. The James Webb Space Telescope represents a leap forward in observational astronomy, with its ability to detect faint signals and resolve fine details that were once beyond our reach. For example, the telescope's coronagraphs, which block out the light from bright objects like stars, allow astronomers to study fainter companions, such as exoplanets or distant galaxies, without the glare of their host stars. This capability has already led to the discovery of new celestial objects and the confirmation of existing ones, proving that the telescope is not just a tool for observation but a gateway to new scientific questions. Beyond the technical achievements, these discoveries carry profound implications for our understanding of the universe's history and future. The images of ancient galaxies, for instance, provide critical data on how galaxies formed and evolved over time. By studying these early structures, scientists can trace the development of the cosmic web, the vast network of galaxies, dark matter, and dark energy that shapes the universe's large-scale structure. Additionally, the detection of heavy elements in young galaxies suggests that the processes of star formation and element creation were more active in the early universe than previously believed. This has important consequences for theories about the life cycles of stars and the distribution of matter throughout the cosmos. Another key aspect of these findings is their potential to address long-standing mysteries in astrophysics. For example, the images of distant galaxies have allowed researchers to refine their estimates of the universe's expansion rate, a topic that has been a subject of debate for decades. By observing the light from these ancient objects, scientists can measure how much the universe has expanded over time, providing crucial data for models of cosmic evolution. Similarly, the detection of specific chemical signatures in distant stars and planets offers clues about the conditions in the early universe and the processes that led to the formation of the elements we see today. These insights are not just academic, they have real-world applications in fields ranging from materials science to planetary exploration. The collaboration between institutions like the University of North Carolina at Chapel Hill and international teams of scientists underscores the global effort to unlock the secrets of the universe. These researchers are not just analyzing images, they are interpreting them within the context of decades of theoretical work and observational data. For example, the discovery of certain features in the images may align with predictions made by cosmological models, while other findings could challenge existing theories and prompt new hypotheses. This interplay between observation and theory is a hallmark of scientific progress, and the Webb Telescope's images are providing a wealth of new data to fuel this process. As the analysis of these images continues, it's clear that the James Webb Space Telescope is not just revealing the past, it's expanding the boundaries of what we can know. The images that have been released are just the beginning, as the telescope's instruments are capable of capturing even more detailed data in the coming years. Scientists are already planning follow-up studies to investigate specific features in the images, such as the distribution of dark matter or the chemical composition of newly formed stars. These studies will require years of analysis, but they promise to yield groundbreaking insights into the universe's history and its future trajectory. In the end, the significance of these discoveries lies not just in what we have seen, but in what they represent, the vast, uncharted territory of the cosmos. The James Webb Space Telescope has opened a new chapter in our exploration of the universe, one that is filled with questions as much as answers. Each image captured by the telescope is a reminder of how much remains to be discovered, and how far human curiosity can take us. As researchers continue to analyze the data, they are not just uncovering the secrets of the universe, they are redefining our place within it. The James Webb Space Telescope, launched in 2021, has already begun to reshape our understanding of the universe. Its ability to peer into the cosmos with unprecedented clarity has revealed distant galaxies, young stars, and the faintest traces of light from the earliest epochs of time. But behind these stunning images lies a complex web of technology, collaboration, and scientific ingenuity. The University of North Carolina at Chapel Hill, among other institutions, has played a pivotal role in interpreting these findings, uncovering the vast potential for discovery that still lies hidden in the data. Let's explore how this process unfolded, from the telescope's design to the breakthroughs that have emerged from its observations. At the heart of the James Webb Space Telescope's mission is its ability to capture light from the universe's most distant objects. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet wavelengths, Webb is optimized for infrared light. This is crucial because the universe is expanding, and light from the earliest galaxies has been stretched over billions of years into the infrared spectrum. To detect this light, Webb is equipped with cutting-edge instruments, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI. These tools are designed to capture faint, redshifted light from galaxies formed just a few 100 million years after the Big Bang. The data collected by these instruments is not just a snapshot of the cosmos, it's a treasure trove of information waiting to be decoded. The collaboration between the James Webb Space Telescope and the University of North Carolina at Chapel Hill began with the challenge of processing and analyzing the vast amounts of data generated by the telescope. Webb's instruments produce an immense volume of information, far exceeding what traditional telescopes could handle. Scientists at UNC, working alongside teams at NASA and other research institutions, develop specialized algorithms to sift through this data, identifying patterns and anomalies that might indicate new discoveries. One of the key breakthroughs came from the use of machine learning techniques, which allowed researchers to automate the detection of faint celestial objects that would have been nearly impossible to spot manually. These algorithms were trained on existing astronomical data, enabling them to recognize subtle signals in Webb's images, such as the faint glow of young stars or the spectral signatures of distant galaxies. But the process of interpreting Webb's data goes beyond computational analysis. The telescope's instruments are calibrated to detect specific wavelengths of light, each corresponding to different physical processes in the universe. For example, the NIRCam captures light in the near-infrared range, which is ideal for studying the formation of stars and galaxies. Meanwhile, MIRI, which operates in the mid-infrared, is particularly useful for observing the cold, dusty regions where stars are born. By combining data from these instruments, scientists can build a more complete picture of cosmic phenomena. One of the most exciting findings from this collaboration has been the discovery of galaxies that formed in the early universe, their light stretched into the infrared spectrum. These galaxies, some of which are over 13 billion light-years away, provide critical insights into the universe's infancy, when the first stars and galaxies were taking shape. The timeline of these discoveries is as remarkable as the findings themselves. The James Webb Space Telescope began its scientific operations in July 2022, and within months, it had already begun to deliver groundbreaking results. However, the process of analyzing these results is ongoing, with new discoveries emerging as researchers refine their methods and improve their models. The University of North Carolina at Chapel Hill has been instrumental in this process, contributing to the development of tools that help scientists interpret the data. For instance, UNC researchers have worked on refining the calibration of Webb's instruments, ensuring that the data collected is as accurate as possible. This level of precision is essential for detecting the faintest signals, such as the light from a planet orbiting a distant star or the chemical composition of a galaxy's atmosphere. One of the most significant challenges in analyzing Webb's data is the sheer scale of the information. The telescope generates terabytes of data each day, requiring powerful computing resources and innovative data management strategies. To address this, scientists have developed specialized software and cloud-based platforms that allow them to store, process, and share data efficiently. These platforms enable researchers from around the world to collaborate in real time, pooling their expertise to tackle complex questions. For example, the discovery of a previously unknown galaxy required not only advanced computational tools but also the collective effort of multiple teams to verify and contextualize the findings. This collaborative approach has been crucial in maximizing the scientific return from Webb's mission. Beyond the technical challenges, the interpretation of Webb's data also involves a deep understanding of astrophysical processes. The light captured by the telescope carries information about the physical conditions of the objects it observes. By analyzing the spectra of this light, breaking it down into its component wavelengths, scientists can determine the temperature, composition, and motion of celestial bodies. For instance, the presence of certain elements in a galaxy's spectrum can indicate the presence of heavy elements formed in previous generations of stars. Similarly, the redshift of light from distant galaxies provides a measure of how far away they are and how fast the universe is expanding. These insights are made possible by the sophisticated instruments aboard Webb and the expertise of the scientists analyzing the data. The University of North Carolina at Chapel Hill has also contributed to the development of new observational techniques that enhance the telescope's capabilities. One such technique involves the use of gravitational lensing, where the gravity of massive objects bends and magnifies the light from distant sources. By combining Webb's high-resolution images with gravitational lensing effects, researchers can study objects that would otherwise be too faint to detect. This method has already led to the discovery of some of the most distant galaxies ever observed, offering a glimpse into the universe's early history. These findings underscore the importance of interdisciplinary collaboration, as the interpretation of Webb's data requires expertise in both observational astronomy and theoretical physics. As the James Webb Space Telescope continues to operate, the potential for discovery remains vast. The data it collects is not just a record of the universe as it is today but a window into its past and a guide to its future. but collaboration between institutions like the University of North Carolina at Chapel Hill and the scientific community at large is essential in unlocking the full potential of this mission. Each new image and dataset brings with it the possibility of answering fundamental questions about the origins of the universe, the formation of galaxies, and the nature of dark matter and dark energy. The process of discovery is as much about the tools we use as it is about the curiosity and ingenuity of the scientists who wield them. In the end, the James Webb Space Telescope is more than a machine, it is a testament to human ingenuity and our relentless quest to understand the cosmos. The images it has sent back are not just beautiful, they are profound, revealing the vastness of what remains to be discovered. The work of scientists at the University of North Carolina at Chapel Hill and their collaborators is a reminder that the universe is full of secrets waiting to be uncovered. As we continue to explore the data from Webb, we are not just observing the cosmos, we are participating in a journey of discovery that will shape our understanding of the universe for generations to come. Webb Telescope images show how much is waiting to be revealed. The University of North Carolina at Chapel Hill. This part of our deep dive into Webb Telescope images show how much is waiting to be revealed. The University of North Carolina at Chapel Hill focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, humanity gazed at the night sky, captivated by the stars, yet unable to peer beyond their shimmering light. The universe was a mystery, its secrets hidden behind cosmic dust, vast distances, and the limits of human vision. But over the past century, a series of groundbreaking discoveries and technological leaps have transformed our understanding of the cosmos. From the first hints of an expanding universe to the breathtaking images of distant galaxies, each milestone has built a foundation for the revelations now unfolding through the James Webb Space Telescope. This chapter traces that journey, exploring how decades of scientific inquiry and innovation have brought us to the brink of uncovering the universe's deepest mysteries. The story begins in the early 20th century, when astronomers first began to grasp the scale of the cosmos. In 1929, Edwin Hubble's observations of distant galaxies revealed that the universe is not static, it is expanding. This discovery, rooted in the redshift of light from distant stars, laid the groundwork for the Big Bang theory. Yet, even as Hubble's findings reshaped cosmology, the tools available to astronomers were limited. Telescopes of the time could only capture visible light, leaving vast regions of the universe shrouded in darkness. Cosmic dust, interstellar gas, and the sheer distance of celestial objects obscured much of what lay beyond our sight. The 1960s and 1970s marked a turning point. The launch of the Cosmic Microwave Background (CMB) Explorer in 1964, led by Arno Penzias and Robert Wilson, provided the first direct evidence of the Big Bang. This faint glow, residual radiation from the universe's infancy, offered a glimpse into its earliest moments. Yet, while the CMB confirmed the universe's origins, it also raised new questions. What came before the Big Bang? How did galaxies form from the primordial soup of energy? These mysteries demanded new tools, and the scientific community began to envision instruments capable of peering deeper into the cosmos than ever before. The 1980s and 1990s saw the rise of space-based observatories, revolutionizing our ability to study the universe. The Hubble Space Telescope, launched in 1990, became a cornerstone of modern astronomy. Its ability to capture high-resolution images of distant galaxies, nebulae, and star-forming regions transformed our view of the cosmos. Hubble's images of the Eagle Nebula's pillars of creation and the intricate structures of galaxy clusters became iconic, but its limitations were clear. Hubble's optical and ultraviolet sensors could not penetrate the thick clouds of interstellar dust that obscured young stars and distant galaxies. To see beyond these barriers, astronomers needed a new approach, one that would require observing in the infrared spectrum. The infrared spectrum holds the key to understanding the universe's hidden realms. Unlike visible light, infrared radiation can pass through cosmic dust, revealing the light of stars and galaxies that are otherwise invisible. This capability became the driving force behind the development of the James Webb Space Telescope. Conceived in the 1990s and approved for construction in the 2000s, Webb was designed to operate primarily in the infrared, with a mirror 6 times larger than Hubble's. Its location at the second Lagrange point, L2, a stable point in space about 1.5 million kilometers from Earth, allowed it to avoid the thermal interference of the Sun, Earth, and Moon. These technological advancements promised to unlock new frontiers in astronomy, but they also came with immense challenges. The telescope's mirror, composed of 18 hexagonal segments, had to be precisely aligned to a fraction of a hair's width, and its instruments had to function at near absolute zero temperatures to detect the faintest signals. The decades leading up to Webb's launch were marked by incremental progress in infrared astronomy. Missions like the Infrared Astronomical Satellite, IRAS, launched in 1983, mapped the infrared sky, revealing the presence of previously unseen objects. The Spitzer Space Telescope, operational from 1999 to 2020, expanded on this work, studying the formation of stars and planets, the structure of galaxies, and the composition of exoplanet atmospheres. Spitzer's discoveries, such as the detection of water vapor in the atmospheres of distant worlds, hinted at the potential for life beyond Earth. Yet, even with these achievements, the limitations of space-based infrared telescopes became apparent. Their relatively small apertures and the constraints of their orbits meant they could not capture the full scale of the universe's most distant and ancient structures. The 2000s brought a new era of cosmic exploration, driven by the convergence of advanced technology and ambitious scientific goals. The European Space Agency's Planck satellite, launched in 2009, provided the most detailed maps of the CMB, refining our understanding of the universe's age, composition, and the nature of dark matter and dark energy. These findings, combined with ground-based observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, allowed astronomers to peer into the earliest epochs of the universe. Yet, even as these instruments expanded our knowledge, the need for a next-generation telescope remained urgent. The James Webb Space Telescope was not just an upgrade, it was a leap forward, designed to address the most pressing questions in astrophysics. The development of Webb was a testament to the patience and persistence of the scientific community. Decades of research, funding battles, and technological innovation culminated in its launch in 2021. Its capabilities far surpassed those of its predecessors. Webb's infrared vision allows it to detect light from galaxies that formed just 200 million years after the Big Bang, offering a window into the universe's infancy. Its ability to resolve the faintest signals from distant stars and planets has already begun to reshape our understanding of star formation, galaxy evolution, and the potential for life beyond Earth. Yet, even as Webb's images captivate the public and scientists alike, they also underscore the vastness of what remains unknown. The telescope's revelations are not just about what we see, they are about what we have yet to discover. The journey from Hubble to Webb is a story of incremental progress, each mission building on the last. The discoveries made by earlier telescopes and space observatories laid the groundwork for Webb's capabilities, but they also highlighted the limitations of our current tools. The universe, as Webb's images now reveal, is far more complex and mysterious than previously imagined. The faint light from the earliest galaxies, the hidden structures within dusty nebulae, and the potential for habitable worlds in the far reaches of the cosmos all point to a universe still waiting to be explored. As scientists analyze the data streaming in from Webb, they are not just uncovering new knowledge, they are redefining the boundaries of what we know. The telescope's images are not just a triumph of technology, they are a reminder of how much remains to be discovered, and how the quest for understanding the cosmos is far from over. The James Webb Space Telescope has opened a new chapter in our exploration of the cosmos, revealing celestial phenomena that challenge our understanding of the universe's origins and evolution. Yet, as its images flood scientific discourse, they also highlight profound mysteries that remain unsolved. These questions are not just about what we see but about the very fabric of reality, dark matter's elusive nature, the formation of the first galaxies, and the enigmatic forces shaping the universe's expansion. The University of North Carolina at Chapel Hill, among other institutions, is at the forefront of analyzing these revelations, but even with the telescope's unparalleled resolution, the answers are far from clear. What we see through Webb's eyes is not a final destination but a gateway to deeper, unresolved questions that continue to shape the frontiers of astrophysics. One of the most striking aspects of Webb's imagery is its ability to peer into the early universe, capturing light from galaxies that formed just a few 100 million years after the Big Bang. These ancient galaxies, often shrouded in dust and gas, were previously obscured by the limitations of earlier telescopes. Now, Webb's infrared capabilities allow scientists to peer through this cosmic veil, revealing structures that were once hidden. Yet, these observations have raised more questions than answers. For instance, how did these galaxies form so quickly? Theories suggest rapid star formation or the influence of dark matter, but the data from Webb's images complicate these models. Some galaxies appear to have matured in less time than expected, hinting at processes we don't yet fully understand. Scientists are now debating whether these observations indicate a faster than anticipated rate of cosmic evolution or if our current models of galaxy formation are incomplete. The University of North Carolina's researchers are among those scrutinizing these anomalies, but the answers remain elusive. Another layer of mystery lies in the distribution of dark matter, the invisible substance that makes up the majority of the universe's mass. While dark matter's gravitational influence is evident in the way galaxies rotate and cluster, its exact nature remains one of the greatest puzzles in physics. Webb's images, particularly those of galaxy clusters, offer new clues. By mapping the bending of light gravitational lensing, scientists can infer the distribution of dark matter. However, the data from Webb's observations sometimes contradict existing models. For example, some clusters show dark matter clumped in ways that don't align with predictions, suggesting that our understanding of its behavior might be missing key components. These discrepancies have sparked debates about whether dark matter interacts with itself in ways we haven't accounted for or if there are alternative explanations altogether. The University of North Carolina's team is actively analyzing these patterns, but the implications of their findings could reshape our understanding of the universe's invisible architecture. Beyond galaxies and dark matter, Webb's images also challenge existing theories about the formation of the first stars and planets. In the early universe, conditions were so extreme that the first stars, massive and short-lived, likely formed in dense, chaotic environments. Yet, the data from Webb's observations of protostars and young planetary systems reveal complexities that defy simple models. For instance, some protostars appear to have formed in environments that were too cold or too diffuse to support their growth, suggesting that our understanding of star formation might be incomplete. Similarly, the discovery of young planets in unexpected locations, such as around stars that are too young for such systems to have formed, has raised questions about the timescales of planetary formation. These findings could imply that planetary systems form much faster than previously thought or that there are alternative mechanisms at play. The University of North Carolina's researchers are contributing to these discussions, but the answers to these questions may require rethinking fundamental principles of astrophysics. The telescope's ability to observe distant galaxies also brings into focus the enigma of the universe's expansion. The Hubble constant, which measures how fast the universe is expanding, has been a subject of debate for decades. Recent observations from Webb have provided new data that could either resolve this discrepancy or deepen it. Some measurements suggest a faster expansion rate than expected, while others align with older models. This inconsistency has led to competing theories about the nature of dark energy, the mysterious force driving the universe's acceleration. If Webb's data supports one interpretation over another, it could either validate existing models or force scientists to revise them entirely. The University of North Carolina's involvement in analyzing these measurements underscores the significance of this debate, but the resolution of this puzzle remains uncertain. Perhaps the most profound mystery lies in the sheer scale of what Webb is revealing. The telescope's images show vast, intricate structures that defy our current understanding of cosmic processes. For example, some observations suggest that galaxies in the early universe were not as isolated as previously thought, with complex interactions between them that hint at a more interconnected cosmos. These interactions could have implications for how galaxies evolved, but the mechanisms driving them are still unclear. Similarly, the presence of unexpected light patterns in some distant objects has led to speculation about new astrophysical phenomena, such as exotic forms of matter or energy that have yet to be explained. These findings, while tantalizing, also highlight the limits of our current knowledge. The University of North Carolina's researchers are among those working to decode these signals, but the answers may lie beyond the reach of even the most advanced instruments. The scientific community is grappling with these mysteries not as isolated puzzles but as interconnected challenges that require collaboration across disciplines. Theories about dark matter, galaxy formation, and cosmic expansion are not siloed, they influence each other in ways that complicate our understanding. For instance, a revised model of dark matter could impact how we interpret the formation of the first galaxies, while new insights into star formation might reshape our understanding of planetary systems. This interplay of ideas means that solving one mystery could unlock others, but it also means that the path to discovery is fraught with uncertainty. The University of North Carolina's role in this collaborative effort is a testament to the complexity of these questions and the need for sustained inquiry. As scientists continue to analyze Webb's data, the telescope's revelations are not just expanding our knowledge but also redefining the boundaries of what we know. The images it captures are not static snapshots but dynamic windows into a universe that is still evolving. Each observation, whether it confirms existing theories or challenges them, contributes to a broader narrative of cosmic exploration. The unresolved questions, far from being obstacles, are the driving force behind scientific progress. They remind us that the universe is not a closed system with all answers already known but an open frontier where curiosity and inquiry are the guiding lights. The University of North Carolina's research, and the work of countless scientists worldwide, is a testament to the enduring human quest to understand the cosmos and the realization that the most profound discoveries often begin with the recognition that there is still so much to learn. As the James Webb Space Telescope continues to unveil the cosmos, its images have become more than just stunning visuals, they're a roadmap to the unknown. Every snapshot of distant galaxies, faint stars, and cosmic phenomena reveals not just what we already know, but how much remains hidden. The University of North Carolina at Chapel Hill's analysis of these images underscores a critical truth: the universe is vast, complex, and full of mysteries waiting to be unraveled. But this is only the beginning. The next chapter of cosmic discovery will be written by a combination of future missions, advanced instruments, and the relentless curiosity of scientists. Let's explore what's coming next and how these efforts could redefine our understanding of the universe. The first wave of follow-up missions will focus on the data already being gathered by the James Webb Telescope. One of the most anticipated projects is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. This telescope, named after the NASA scientist who championed the idea, will complement Webb's work by surveying the universe in visible and near-infrared light. Its primary mission is to map dark matter, the invisible force that shapes the structure of the cosmos. By observing how light bends around massive objects, Roman will help scientists create detailed maps of dark matter distribution. These maps, combined with Webb's infrared data, could reveal how dark matter interacts with galaxies and whether it behaves differently than previously thought. Such insights might challenge existing models of cosmic evolution, pushing us closer to understanding the fundamental forces that govern the universe. Another key player in the coming years is the SphereX mission, a NASA-led project set to launch in the early 2020s. SphereX will conduct a full-sky survey of the universe's light, focusing on the faintest and most distant objects. Its unique approach is to analyze the spectrum of light from millions of galaxies, searching for subtle variations that could indicate the presence of dark energy. Dark energy, the mysterious force driving the universe's accelerated expansion, remains one of the greatest enigmas in modern physics. By measuring how the light from distant galaxies shifts over time, SphereX could provide critical clues about the nature of dark energy. If the mission detects deviations from current theories, it might force scientists to reconsider the equations that describe the universe's fate. These findings could either confirm existing models or open the door to entirely new physics, reshaping our understanding of the cosmos. Meanwhile, the European Space Agency's Euclid mission, scheduled for launch in the early 2020s, will take a different but complementary approach. Euclid will focus on the large-scale structure of the universe, using its advanced cameras and spectrographs to study how galaxies cluster and evolve over time. By mapping the distribution of matter across billions of light-years, Euclid will help scientists trace the influence of dark energy and dark matter. The mission's data will be combined with observations from the James Webb Telescope, creating a multi-wavelength picture of the universe's history. This synergy could reveal how the interplay between dark energy and dark matter has shaped the cosmos, potentially uncovering new phenomena that challenge existing theories. For example, if Euclid detects unexpected patterns in galaxy distribution, it might hint at unknown forces or interactions that have yet to be discovered. Beyond space-based missions, ground-based observatories are also preparing to play a crucial role in the next era of cosmic exploration. The Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of Chile, will be the largest optical telescope ever built. With a mirror over 39 meters in diameter, the ELT will capture light from the earliest stars and galaxies, providing unprecedented detail. Its advanced instruments will analyze the chemical composition of distant stars, helping scientists determine how elements like carbon and oxygen formed in the universe. These observations could shed light on the processes that led to the formation of planets and life itself. Similarly, the Giant Magellan Telescope, GMT, set to begin operations in the 2020s, will use a combination of massive mirrors to achieve resolutions comparable to space telescopes. The GMT will focus on exoplanets, searching for signs of atmospheres and potential habitability, while also studying the early universe to uncover the secrets of the first galaxies. The James Webb Telescope itself will remain a central player in these efforts. While its primary mission has already yielded groundbreaking discoveries, its extended operations will allow scientists to delve deeper into the data it has already collected. For example, researchers are already working on follow-up studies of the faint, distant galaxies first detected by Webb. These galaxies, some of which are over 13 billion light-years away, may hold clues about the universe's earliest moments. By studying their light in greater detail, scientists could determine how the first stars and galaxies formed, whether they behaved differently than expected, and how they influenced the development of the cosmos. Additionally, Webb's observations of star-forming regions could reveal new insights into the processes that birth stars and planetary systems, potentially challenging existing models of stellar evolution. However, the future of cosmic discovery is not without its challenges. One of the most exciting possibilities is that these missions could uncover phenomena that defy current scientific understanding. For instance, if the James Webb Telescope or its successors detect objects that do not fit within the framework of existing theories, such as stars that form without massive gas clouds or galaxies that defy the laws of gravity, scientists may be forced to rethink the fundamental principles that govern the universe. Such discoveries could lead to the development of new theories or even the revision of long-held assumptions about the nature of dark matter, dark energy, and the structure of spacetime. The universe has a way of surprising us, and the next few decades may bring revelations that reshape our understanding of reality itself. Another area of potential breakthrough is the search for life beyond Earth. While the James Webb Telescope has already begun to analyze the atmospheres of exoplanets, future missions will expand this effort. The Plato mission, led by the European Space Agency, will search for Earth-like planets in the habitable zones of nearby stars, while the James Webb Telescope's successor, the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, could provide even more detailed atmospheric data. These missions will look for biosignatures, molecular markers that indicate the presence of life, such as oxygen, methane, or other complex organic compounds. If such signals are detected, it could mark one of the most profound discoveries in human history, proving that life exists beyond our planet and raising questions about its origins and diversity. The collaboration between these missions will be essential in piecing together the puzzle of the universe. Each telescope, instrument, and observation will contribute a unique piece of the larger picture, creating a more complete understanding of the cosmos. For example, the data from the James Webb Telescope will be combined with the surveys of the Roman Space Telescope and Euclid to build a comprehensive map of dark matter and dark energy. Similarly, ground-based observatories will provide high-resolution details that complement the broader surveys conducted by space telescopes. This synergy will allow scientists to cross-check findings, identify patterns, and refine their models, ensuring that each discovery builds on the last. As we look to the future, it's clear that the universe is far from being fully understood. The images captured by the James Webb Telescope have shown us that there is still so much to learn, and the next wave of missions will take us closer to answering some of the most fundamental questions about our place in the cosmos. Whether it's unraveling the mysteries of dark matter, detecting the signatures of life, or discovering phenomena that challenge our current understanding, the coming years promise to be an era of profound discovery. The universe has always been a vast, mysterious expanse, but with each new mission and observation, we take another step toward unlocking its secrets. And as the James Webb Telescope continues to peer into the depths of space, it reminds us that the greatest discoveries often lie just beyond the horizon, waiting to be revealed. The James Webb Space Telescope's images are doing more than just capturing distant galaxies, they're revealing the universe's hidden depths, proving how much remains to be discovered. These images, processed by institutions like the University of North Carolina at Chapel Hill, show galaxies forming in the early universe, their light traveling billions of years to reach us. What's most striking isn't just the scale of these cosmic landscapes but the sheer number of objects waiting to be studied. Some of these galaxies are so faint and distant that they've never been observed before, challenging our understanding of how the universe evolved. The Webb Telescope's advanced instruments, designed to detect infrared light, are uncovering details about star-forming regions, ancient stellar systems, and even potential exoplanets that were previously invisible. This isn't just about seeing further, it's about seeing differently, peering into the cosmos' earliest moments and uncovering secrets that could rewrite our cosmic timeline. One of the most profound takeaways is how these images highlight the universe's vastness. The faint glimmers in the Webb Telescope's data might represent entire galaxies, each teeming with stars and planets, many of which may never be studied. This underscores a fundamental truth: we've only scratched the surface of what exists. Another key insight is the role of collaboration in unlocking these discoveries. Scientists at UNC Chapel Hill and other institutions are working tirelessly to process and interpret the data, combining cutting-edge technology with decades of astronomical research. Their work shows that even with the most advanced tools, the cosmos still holds surprises. For example, the telescope's ability to detect light from galaxies formed just a few 100 million years after the Big Bang is reshaping our understanding of cosmic evolution. These galaxies, once thought to be rare, are now appearing in abundance, suggesting our models of star formation and galaxy growth may need revision. Perhaps most exciting is the potential for these images to spark new questions. The Webb Telescope isn't just answering old mysteries, it's raising new ones. What lies beyond the edges of these images? Are there structures we've never imagined, like dark matter filaments or unknown celestial phenomena? The data is a treasure trove, but it's also a puzzle, inviting scientists and the public alike to wonder what's next. This deep dive has shown that the Webb Telescope isn't just a tool for observation, it's a gateway to the unknown. Every image is a reminder that the universe is far more complex and mysterious than we once believed. The collaboration between institutions like UNC Chapel Hill and NASA exemplifies how science thrives on shared curiosity and innovation. As we continue to analyze these images, we're not just learning about the cosmos, we're learning about our place in it. The universe has always been a vast, enigmatic expanse, but the Webb Telescope is proving that its secrets are still unfolding. For those who follow this journey, the takeaway is clear: the cosmos is full of surprises, and the best is yet to come. If you've enjoyed this glimpse into the Webb Telescope's revelations, consider subscribing to FactVerse for daily deep dives into the mysteries of space. Whether you're a seasoned astronomy enthusiast or simply curious about the universe, there's always more to discover. And if you have your own theories or questions about what these images might mean, we'd love to hear from you. The universe is waiting, and so are we. Let's keep exploring together.